So today is we have come to the
we
have come to the heart of the matter with the proof. So let me just remind the general setup. So we have our model W. Which is a finite set with relation R, which is irreflexive transitive, and a series or family of relations S labeled by nodes, points in W. These are transitive, reflexive binary relations, and there are certain conditions on it. Most importantly, Sx is a relation essentially defined on the R successors of X. So its domain of Sx is the nodes that are above X, and also we have this principle that R. So Rs entails R,
right?
And S, I guess SR also entails R, something like that. We have this. Okay, and of course we have certain evaluation of variables on that model, but we have done already during the last lecture everything we needed to know about formulas and variables. So we reduced the proof of our theorem to a construction of a certain, let's say, family of sentences associated with, again, points in our model. So to every point we associate the sentence lambda x. And they should satisfy certain properties. So a model we usually picture a little bit like that. So we can, with every x, we associate the sentence lambda x. We also assume that our initial root is 0, so the formula is that we want to eventually interpret is false at node 1, but basically we forget everything about the internal structural formulas, but we think in terms of this lambda x's. So they should be, in particular, mutually exclusive, and disjunction of them should be provable. And this will be achieved by saying that lambda x is, by definition, saying that limit of the function g is x. G is a function, let's say, from omega to our set W. So the limit of the function from omega to W, if the limit is in x, then lambda x holds. That guarantees more or less this property that and the function will be such that we will be able to prove that the limit exists. And we are working with a theory T, which is a theory which is sigma 1 sound and contains I sigma 1. So that's basic assumptions for our theory. And before presenting the construction, let me perhaps begin with a simple, well-known lemma, which is used throughout the proof all the time, which is called small reflection. So it's about probability.
Well, sorry. Actually, as far as I remember, the thing that remained to be proved is that providing some such function which satisfies 4 or 5 properties.
Main properties are 4, so 2 of them I already gave.
Yeah, we did this function.
Yeah,
but, okay.
And so we need to verify 4 significant properties, and I will remind them as a 4 additional lemmas. So
okay.
But we precede this dealing with these properties just with a general lemma, which is very useful in many, let's say, dealings with arithmetic. So the first, it says like this. So for every n, the theory T proves so for every sentence phi and every natural number n, our theory T proves reflection. For proofs, you can say for proofs less than n, but here it is stated just for the proof encoded by n. Like that. We could have written here like reason x smaller than n. That's essentially the same thing because this premise, this is a numeral, therefore this is a kind of disjunction of instances for all numbers, and this reduces to application of that point n times. So that's called small reflection. And item 2 is the fact that it is formalizable in T itself. So T proves that for every n and x is provable in T that n x, so even with the parameter, if you like, you can say phi of x d holds like that. So here I forgot what I used, notation I used. So basically n and x here now are just number variables. And underlining means that we are in fact using so associate with every number n, the nth numeral, and it is substituted here in this formula. So T proves that for every specific numbers n and x, it is provable in T, namely what is written here. So what is here is more or less a direct formalization of what is written here. So that's one thing. So the reasoning for item 1 and for item 2, they are more or less the same. So let's prove it. Proof of item 2. Right, so here we reason like this, reason in T, so T proves it. If not, we have T of n phi of x. Well, maybe I should have written like that. So if it is not provable, if phi of x is not provable, then this fact is provable in T. Because this is a sigma 1
complete
formula, in fact delta 0 formula. And then from this box, if box of negation, then negation implies inconsistency, inconsistency implies phi of x. So then box T, what is needed to prove? And similarly, if PRF T of n then we can just say we put existential quantifier over this n, and this will become box. So then box t phi of x, and then box t and the weaker statement of the lemma. So if phi of x is provable, then multiplication is provable. So this also holds. So regardless of which one of these assumptions holds, we infer the statement. So this is reasoning very elementary. Uses only sigma 1 completeness, so it is in T. And of course, from item 2, you infer item 1. That's
so this argument essentially works for any sigma 1 complete theory T.
yeah. Right. Right.
Well, classical.
Right.
Intuitionistically,
essentially so. Essentially so. Right. Yeah. Good. So from there we begin with, let's say, let's do the following. We now reproduce the definition of our function g. That's the important thing. So maybe I will even use the same clipboard. No, wait, wait. Let's write the definition of the function g. And this is preceded by, again, I'm repeating the very end of the last lecture. So we define the formula. The function g will be primitive recursive or even elementary, so that's kind of assumed. And assuming we have this defined such a function g, we can define formulas delta wu of n. W and u are nodes here, which will be kind of typically W and U. There will be nodes related by, well, in this mode. So in typical case, there will be R arrow between W and U. So the formula is saying the following. There is a T bigger than N, such that G of T is N. Is U, and for all z less than t, if n is d, then g of z is w. Okay.
So I'm still stuck on the second item. So,
second item here.
yes, what is this sentence when you write it out? Because for all nx and then the numerals.
Yeah, this is the formula. So phi is a formula with a free variable.
Yes.
In the free variable x, you can substitute the numeral.
Yes.
0 s x times.
Yes.
So then there is this primitive recursive term
Yes.
of x denoting the Gödel number of the result of substitution in phi, the numeral for x. And this is exactly what is written here.
Okay.
So that's a certain, here we see in fact certain primitive recursive term t of x, which is traditionally denoted like this because the meaning of this, the value of this term is the formula which is the result of substituting in phi numeral for x. Yeah, notations here are horrible, but this is a part of the sort of part of the fun of arithmetization. So this is a good old. But again, the meaning of that is exactly what is written here. For every number n, the formula of the form like this and this is the actual numeral for n, is provable in T. And the reasoning is like this. If this is true, then phi is provable, then the implication is provable. If, or rather like this, if this is false, then it is actually disprovable because it's delta 0, and then the implication is also true. And that's what is written here in this more formalized way. And by the way, it's good that I did this because within this Japaridis proof, as well as within his paper, it would be horrible if we actually wrote down all the proofs on that level of formalization. Although they should, formally speaking, be looking like that, it will be not understandable. Now, what he in fact does, as many people also do, they replace this type of arguments by this type of arguments. So, by saying reason in the theory T, and then they produce an informal argument in T, and saying, okay, this is an argument, in fact, formalizable in T, so we like that. So in this way, we are dealing with a kind of nested proof system. And the nesting occurs when we are going to show something within a box. We sort of open the square bracket and then produce a contential argument, contential proof there, and then close the bracket. But the result of that we have proved box of something. So that's a nested proof calculus.
Nested.
That is used here all the time. So it's very essential that we do it like that. So I will also practice this thing. So de facto it leads to, instead of writing such things, you write just such things, which is shorter and clear. So, and instead of PRF and T5, what would we write? Well, that's a predicate that N is a proof of phi in T. So usually we write it like T proves phi, but if we want to stress that this proof has Gödel number N, we will just write it like that. So informally, it is this, and this is a arithmetization of that relation. Okay. Good. So that's one remark. So we have defined our delta. So informally, delta says that the function g,
which is not defined yet.
It is not defined yet. So it depends on what g actually is.
Right.
We could have written it like g, but g will be one and the same function all the time.
Right.
So we say that basically the following: that at the point of time n, our function g is in W, and then sometime in the future, at the point t of time, it jumps from W to U.
Exactly.
And that's sort of in one go. And that happens sometime after n. That's the intended meaning. And you see that this is a sigma 1 formula. So that's the important thing. So this is an unbounded quantifier, and this is bounded quantifier. So this is sigma 1.
G, if G is itself sigma 1?
Primitive recursive.
Ah, it is primitive recursive.
Oh, yes, even elementary. Okay, so that's one thing. Another thing, another piece of notation is we have truth definition for sigma 1 formulas, right? So the standard sigma 1 formula, which defines the truth for sigma 1 formulas, but we will sort of write it down in a more explicit way like this. where this formula wit is essentially saying that X is a witness for this sigma 1 formula denoted by N, with the code N, and the witnessing predicate is already primitive recursive, right? So we can also assume that it is lambda. So we sort of, as Japaridze writes in his paper, so this is a standard witness for the sigma 1 sentence. X is a standard witness in the sense that it refers to this truth predicate, which is one and the same predicate for all sigma 1 sentences. Well, anyway, so that's what we introduce. And we will be referring to these witnesses when we define G. Now let's go to the definition of G. Let's go to the definition of G. And here is the main definition for today. So, of course, G of 0 is 0. And suppose that G of y is defined for all y before x, and G of x is w. Then we define what G does by two items. Item G1 is kind of easy one. So if we encounter, if x, so x is the current time, right, current moment of time. So if x is in fact a proof of the implication of the form not delta of w u of n for some numeral n, for some n with n less than x, with n less than x, and w are u, and for all z in the interval from n to x, G of u is in fact in w. Then G of x plus 1 is u. So here is the part of the definition 1. So the explanation is this. So we encounter a proof that the limit statement lambda u for some u above w. So it's like the standard Solovay construction. U is a node above w, and we encountered that lambda u implies something, that delta is false. In the original construction, we just used contradiction here. If x is a proof of not lambda u, then we must jump. So here we just react to the weaker implications. Lambda u implies something unwanted, and this unwanted statement is precisely the negation of our delta. So our delta is telling us that the function was at w up until it jumps immediately to u. Right?
Well, I can read the contraposition in a little bit, well, at least more intuitive.
No.
Okay.
Wrong move.
Well, I better understand that way.
No, okay, but, yeah, but I would say it's important to make it this way.
Okay. I wouldn't disturb it.
Because then we will have to switch back.
All right.
But anyway, but the point is this. The precondition for this move is that from a certain moment n up to x, our function g was in fact in W. So from n to x, without any changes, function g was in W. So, and then we order our function to jump immediately to u. Thereby we making the sentence delta of W u of n true. And our proof will be in fact of a proof of something false. Right? So thinking kind of retroactively, we encounter a proof in our theory that our function cannot go immediately from W to U. It cannot go. So the theory thinks that it cannot go, and then we say, no, we will make it go immediately to U, and we go immediately to U. So that's the main, one of the tricks. So we make it false. So in the original Solovay construction here, what we did, we encountered a proof that this is not a limit. And then we jumped to that point, sort of making it possible to be a limit. But, so here it's more dramatic. So we just make the conclusion false. So here the conclusion was, if it's contradiction anyway. So this is the item 1 in this program for the function g, and item 2 is this one. So if otherwise, so priority is on move like g1, and move steps like g2 happen only if g1 is not possible. Otherwise, if there exists an n less than x, and there exists a pi, one sentence pi small, and u such that satisfying certain conditions, again, M is a proof that lambda u implies pi. So now we are looking at proofs smaller or equal x. So proofs, again, that lambda u implies something, but now we're considering arbitrary pi1 formulas, but not arbitrary, but those which are false and in fact witnessed before x. In other words, there is a z less than x such that v equals of z not pi. Here is another condition. W S G of M U. So the nodes U that we consider amenable to all these conditions are those. So this M for which we smaller than x, for which we encounter the proof, actually points us to the value of g in the past, right? So currently we are at x. So current moment of time is x. And this condition tells us that in the past, before x, there was a certain moment of time when we received a proof m of a false pi1 statement. And at the same moment of time, our function g was in a certain world in our frame, so that the relation, there was an S arrow from W to U. Okay? W was the current value of G in the current. So looking from the past, so this was the word G of M, that means that there was something like R arrow to the word W, and then there was this S arrow with S G of M arrow to the word U, which was also R, reachable from G of M. So what it tells me, my understanding of this condition, we will see how it works. So when we have an R arrow between two nodes, so the story of this function is that there should be many steps, many steps before something R below and something R above. So from the point of view of let's say lambda G of M, the moment that we jump to W can only be a non-standard moment of time, something like this. So there is a big difference here. So in some sense, this tells you that this M is very small compared to X. So that's my intuition. So maybe but we will see. So and condition D is very easy. M is minimal possible, satisfying all the previous conditions. So we can only, so there are conditions A, B, C, D, and of course if they are all satisfied, then we say that G of X plus 1.
So can you read again the conditions? Can you read again the condition D?
Condition D is M is minimal possible among all the tuples M, pi, U, satisfying conditions A, B, C.
Oh,
yeah. Just to select one specific.
yeah.
And this thing is called then the rank of the S move. So if such a thing happens, we call it an S move, and this was an R move, and S moves they have ranks, namely these strange parameters M smaller than the current moment of time, which satisfy all these preconditions. Yeah, so you see that this is an incredibly tricky thing. But okay, so that's the definition of G2, and okay, G3 is otherwise put G of X plus 1 equals G of X. So G does not move. And you see that this is a primitive recursive in fact. So this combination of all these conditions, these are all primitive recursive conditions, because they are something about the existence of proofs below X. So everything is checkable primitively recursively. So this step from X to X plus 1 is primitive recursive, but of course in the Gödel number of the function G itself. And fixed point theorem tells you that there exists such a primitive recursive function g satisfying all these conditions. With respect to proofs, where these proofs refer to, in fact, the same function g itself. So that's a kind of involved application of a fixed point construction. Okay, that was.
It's supposed to be point. So you also want it to be sigma 1, right?
What did we want to be sigma 1?
So as we were saying, so if you want the deltas to be sigma 1, you are basically like saying that G is a sigma 1.
In fact, it will be a primitive recursive function. Therefore, this one will be sigma 1.
So my point would be, so if you want to, okay, so the lambda x, like the immediate definition that comes to mind, that's not sigma 1.
Lambda x are not sigma 1, they cannot be sigma 1.
Okay.
Lambda x are not sigma 1, but they
are
are occurring within the proof predicate. So if you decipher this on the dual level of formalization, this will be PRF x something, and PRF is primitive recursive. So, and this will be PRF m for m smaller than x. So this is kind of informal explanation of a formal primitive recursive definition, to which then you can apply the fixed point theorem and get everything you need. So that's so you see. So there are different mechanisms here in these definitions that are somehow working. So let's prove several properties. So first lemma 1 if g of x is r w, and then for all y small x, g of y r w. Yes, so if our function g at moment x is somewhere and w is r above that, that means that all the previous history of the function g was also r below w. This is simply the property of these frame conditions that we have. Formally speaking, we can prove it by sort of descending recursion from x downwards. So g of x rw is my assumption, and if we have, for example, g of x minus 1, then it is either coincides with g of x if g3 condition was, or it is s g of x rw, and in this case we have also an r arrow here, or it is r. Then on transitivity you also have r. So that's is it understandable here? So that's just the property of our moves and the conditions on arrows. So rs means r. So that's the point. And this is, of course, so elementary that it is provable in our system T, in our theory T. So that's good. Lemma 2. This is already a little bit more interesting. So for all m and w, t plus lambda w proves the following effect. No S move to W can have rank smaller than M. So for every number m and point w, the theory T plus the assumption lambda w, so our typical reasoning will be in the theories T plus lambda w. So T plus lambda w cannot proves, in fact knows, that no S move to W can have rank smaller than M. In other words, the rank of this S move can only be non-standard. Now, why so? Okay. Reason in T plus lambda. If G moves to W with rank smaller than N, then what does it mean? So we look at our conditions. That means that we are in condition G2, and this M will actually be smaller. This M here will be smaller than MZ. So the rank of that proof, so the number of that proof will be smaller than that standard number M here. So here small reflection tells us, okay, so then there is a false pi1 sentence, and there is an x smaller than 0, such that we are ft x. I promised to write you in a less formal way, but let's do it. So if G moves to W with rank less than M, that means that we have obtained this crucial proof A. Certain proof, certain pi1 sentence, and a proof from lambda u of that pi1 sentence, and that pi1 sentence must have a witness smaller than x, right? In particular, it must be false. Okay. But this M is standard. That means that there are only finitely many proofs, possible proofs like that, smaller than M. And in particular, there can this sentence pi, of course, is also smaller than the good number of the full proof. So you can say that there are only finitely many possibilities for such a pi here. All of them smaller than M. And for each of them, we will have this condition. So by small reflection, from this we can infer that lambda w implies pi I for each I. And of course this implies not pi I for each of these standardly many i's of I 0 up to k. And so, yeah. But we are reasoning within the theory T plus lambda w, so let's say lambda w, assuming lambda w, we have lambda w also as true, and then it follows that pi I should be true, but it is false, so contradiction. Right.
Yeah, what is pi I again?
Yeah, so important point is that m is a standard number,
Yes.
so it's like 17. And below the number 17, there are only finitely many pi 1 sentences. So
Okay.
we list all of them. For every specific pi 1 sentence, we got a number less than 17. If there is a proof of lambda w implies pi I, then this thing should be true by small reflection. And if it is true, we also assume lambda w, then pi I is also true. But truth of pi I implies negation of, well, the other part tells us that not pi I is true. So pi I, we get pi I, not pi I contradiction. So for every I from 0 to k, we in fact infer a contradiction. So from disjunction, so this bounded existential quantifier will be equivalent to disjunction of all these sentences for every I. And for each of the disjunct, we infer the contradiction, so we infer a contradiction. So that's basically the kind of reasoning here. So we therefore arrived the hypothesis that the rank was smaller than m leads to contradiction. Okay, so lemma 2 is proved. So now let's look at the let's say lemma 3, the limit of G exists. The limit of G exists. So how do we argue here? So so the function G moves along the arrows in our model, and it's either S steps or R steps. And there cannot be infinitely many R steps because the model is finite and R is irreflexive. So whatever the S steps, you cannot have more than finitely many, boundedly many R steps. So let's consider the moment of time. So in this whole evolution of the function G, the tail will consist only of S steps. So if there is an infinite tail, there will be only S steps after a certain time. And if we have only S steps, then we notice the following, that in fact every other S step is actually, can only have smaller rank, so consecutive S steps actually lead to, well, they have smaller and smaller and smaller ranks. So this M, every mu M, should be actually smaller than the previous M, because we selected here all the times the minimal possible proof satisfying certain conditions, and these conditions sort of continue to be satisfied. So all these so the setup is that consecutive S steps will have diminishing ranks, and then induction will guarantee that sooner or later there will be either there will be just S steps kind of cycling in one and the same point, so, or there simply will be there will be item G3 all the time. In other words, the limit will be attained. Okay. So let's how much time do we have left? Maybe okay. I think we will be able to do 2 lemmas and in the remaining time, and then we will leave the last part for the last time. So that will be so. Again, so let's do the box lemmas. They are somewhat okay. Let's do the box. Lemma 3, lemma 4. So if W are U, then T plus lambda W must prove that lambda U is consistent with T. So that's the same thing as with Solovay. So if the limit is W, then it is not provable that the limit is not U for any U which is R visible from W. Okay, so this one is easy. So suppose, again, reason in this theory. So suppose for all x bigger than n, g of x is so assuming lambda w, there exists an n, so that after n the function is w. If t proves not lambda u, so assume otherwise, that t proves that disproves lambda u, then there is an x which we can assume bigger than n, such that x is a proof in T of lambda u implies delta w u of n. So every statement like this one has arbitrarily long proofs. And so we just pick any proof which is bigger than n. But we can, it will be, I guess, bigger than n anyway, because numeral n is kind of part of that proof. Okay. So if good numbering is reasonable, then this x will be bigger than n anyway. So there exists a proof of, so lambda u was, so we assume that t proves lambda u implies bottom. From that proof, one can concoct such a proof, and it will be our proof x. Yeah, then we simply must go to u. Because condition G1 is satisfied for this particular, yes.
So I think you forgot not.
Huh?
So not delta W.
Not delta, not delta. Not delta. We need to satisfy the condition, very good. And right. Then with not delta we will have so that's it. So lemma, a contradiction, and that means that we proved what was needed. Now second, lemma 5. So if W is not 0 and W does not exceed u, then T plus lambda W proves box T not That was the second old condition. We sort of recovered the old conditions of Solovay, but with a new definition, let's say a spoiled definition of the function. Okay. So here, let us maybe here. So there are two cases to consider. So case one. U is W. So kind of a simple case. U is W. Then we of course reason assuming lambda W. Assume lambda W. Then there exists in X such that G of X is V, which is not U, and G of X plus 1 is U. So at a certain point of time, our function jumped
to U.
To U.
Or
Yeah, because U is double. And we assume that lambda double. Okay? So we assume that the limit of the function is W, but W is U. So let's fix the moment when the function came to this point U. And it came to U from a certain point V. So we have this V, and we have here U. That's what we know. We don't even know what kind of
Movies.
transition this was. Yes, indeed. Indeed. So there are two possibilities. The possibility A is this was an R transition. VR. An R transition. Then, by the definition of R moves, we must have at the point X, which we already know that this is X, and X is a proof of lambda U implies not delta of V U of N. For a certain N. And delta V U of N is true.
Yeah. By assumption, yeah.
Yeah, because precondition for this move is precisely, as I said, that it makes the fact that we have proved false. So this precondition implies the falsity of not delta, so delta is true.
No, actually, the truth of delta VU comes from that existential quantification above that. Actually, you assumed that this should be true. Well,
this is all our assumption.
Yeah,
That we actually moved from V to U.
At the point.
Therefore, it is true.
Yeah.
Okay, but it is a sigma 1 formula. delta is sigma 1. So in fact T proves, then T proves delta V U of M. Hence T proves not delta V because of the contraposition that which time I wanted to do at the very beginning. But we still have case B to consider. So case B is the following case, that this is an S move. S transition. Okay, what can we say? Then, by the conditions for S transition, there is a proof of a certain false pi 1 sentence. Then there is a pi, and then there is a pi such that T plus lambda U.
You did not consider the case that W. Oh, okay.
T plus lambda U proves pi. I'm not writing all the conditions, just those needed here. So T plus lambda U proves pi, and it is witnessed before x. That means that in fact pi is false, and pi is false. Okay. But then, by sigma 1 completeness, this is also sigma 1, T proves not pi, so basically, and if T proves not pi and T plus lambda U proves pi, and that means that T proves not lambda. So, same thing, kind of similar. Right, so we are done with A and B, but there is case 2. To consider the main case where U is not double. So let's do the next reasoning. So let's case 2. U is not double.
Actually, above W is the interesting case. Above W is the only interesting case. Below W is obviously we have the negation of lambda U, right? In any. Well,
So we assumed lambda W. So
assume lambda W, and then you have box T of not lambda U for any U below W, obviously, by sigma 1 completeness.
right.
And the fact that it is. Maybe
So
you don't. It doesn't simplify your argument.
But anyway, let's see what we have here. So it's okay. I assume G of Z is W. So our function G was in W at a certain point Z, and then we can also verify this in T. With numerals. I'm sometimes omitting the numerals under the names of the worlds because there are only boundedly many of them, so they're kind of numerals anyway, but other numbers may be numerals, maybe not, and this is somehow important here. And now we open the bracket and say reason in T plus lambda U. So we need to prove a contradiction, so we reason in T plus lambda u towards a contradiction. Okay. Since G of z equals W, which is not u, we have that there is a z, there is an x such that g of x is not u, and g of x plus 1 is. So at a certain point we came to the point u, and this one will be after we came to w. After we came to w. So since w is g of z, so since we do not have this relation, we have this important for all y between z and x, g of y is not r. So from g of y we do not see u by r. Why so? Because again, by that lemma number 1 that we have. So if for any of that we have g of y r u, then for every previous steps we will also see the point u, but we have w, which is g of z. This is not so. So by lemma 1. I think I need a picture, right? So I need some picture. But okay, so what do we have here? So we have our point W, which will be the lowest node W. We have U, which is somehow not reachable from W by R. That's the assumption. And what we did, we nevertheless we assumed that somehow we came to U. We came to U. And this happened at a certain moment X. So at the moment X we came immediately to U, and everywhere, so G of, so at the moment Z we were in W, and somewhere later in X we came to U. Okay, that's the point. Yeah, in particular, G of X not R U, because this is for all y, so including X, and this means that this transition to U was from somewhere by S step. Then we claim that the rank of S transition to U has to be a certain number m smaller than Z. Now, why so? Because when we make this transition, so this happens at a point x in time. And that means that this rank M, so remember the picture that we have there. So there should be, so this rank, let's call it R. This rank R is such that from the point G of R, we see both of these points by R. Both of these points by R. And this means that this R should be below Z, because here we don't have any R relations with U. So this rank R transition to U is a certain number M, strictly smaller than Z. That's the crucial, in fact, observation in the whole construction, because Z here, in fact, is a standard number. You see, so it is underlined everywhere. And then, by lemma 2, we know this, in fact, contradicts lemma 2. Okay, because lemma 2 says that no S move to U, in this case, T plus lambda U proves that no S move to U can have rank smaller than M, any standard number. And we have here a standard number. By lemma 2, we obtain contradiction. Bracket closed, so this was a reasoning in T plus lambda U, assuming lambda U, and we obtained a contradiction, so our lemma is proved. Right, I think so. For today, it's the right amount for today. So basically, it's only two statements to be proved. Of them, one is really simple, so it could be done in 5 minutes, but we will postpone it till next time. And the other one is somewhat more complicated than this lemma. So
the one concerning the SW relation, right?
Yeah.
The condition.
Yeah. Well, there are two steps, two S steps, so to say, two S conditions, to positive and negative, and the one which was one of them is again kind of negative condition is easy, but positive condition requires some considerable analysis, as far as I can see. So that will be postponed till next time. But it's good if we can ask any questions about all this setup so far.
As far as I remember, the construction, well, essentially, as far as I remember, the Berarducci's construction is quite similar to this one, the Solovay function at least. It also includes some such condition regarding the, well, can you bring that definition up again, so that I can point at? Well, in the condition G2 in C, actually the same actually condition between which I guess it refers to the interpretability.
As far as I remember, so there are slight differences. Namely, Berarducci referred to, by ranks of proofs, he actually referred to ranks of subtheories of PA. So you consider proofs, let's say from
right, yes, that's true.
From finite subseries of PA, and then with these finite subseries of PA, you sort of define the notion of rank.
But that subtheory also is in in a condition, for instance, it appears. The M provable.
There is no subtheory here, so that's an important difference, because PA was reflexive. So PA is infinitely excellent. There is this hierarchy of subseries proving reflection over one another. But here we are not So we are working over a finitely axiomatized system, T, like I sigma 1.
Right. Okay.
But we are referring just to the numbers of proofs. So instead of essentially this reflection over finite subseries, which is also valid principle, but stronger and playing perhaps a similar role as here with small reflection. So here a small reflection replaces this actual reflection for finite subseries. So I guess this is somewhat simpler. And of course it does not involve any, how do you call it, talk about ACA0, formalizing model theoretic arguments in ACA0, etc. which is So also I'm not sure about this condition, the role of these sentences. So here
that does not appear there. I remember such thing does not exist, but it can be. Well, it is just a handy definition to simplify.
No, but basically the conclusion. Of course, all these constructions are derivative of Berarducci and or Shautov's construction was also different, but using similar kind of general ideas. Right. So general idea is this witness comparison of Rosser-like sentences with truth definitions, like in that Lindström lemma that I proved at the first lecture in the series. So we kind of compare, so the crucial tool was here to compare these witnesses of false sigma sentences with proofs of, you can say, false statements or something like this. So it's proofs of statements of a certain kind. And which one of them happens first determines for you somehow what you eventually do here. But if you ask me, I wouldn't be able to invent this proof kind of from general principles that I understand. So this is clearly clearly some fine-tuned machinery. For example, why was it necessary to actually replace? So here we have the feature that the theory reacts not to limit statements, but to proofs of something from limit statements. With respect to pi1 sentences, this is kind of natural because we establish conservativity, and there we need to achieve that certain pi1 sentences are not provable from something, so like that, or provable or unprovable. Anyway, proofs like that are kind of natural to occur in the construction, but the fact that one should mix them up with these delta statements, I think is nice. So this is a kind of interesting mechanism. So all right.
Okay, thank you very much. I have one question.
Yes.
So could we use here in this theorem simplified research frames? Would it be easier?
I think we can. It will not be easier. Because, well, I think that simplified research frames, they serve as well. So they're infinite, but they're well-founded, and you can assume that your theory proves their primitive recursive well-foundedness, and that's sufficient for the existence of limits. So the important thing is that the theory is able to prove the existence of limits. So for I sigma 1, I would guess it also should work. But on the other hand, here what you see the role of these relations as W, because they sort of mark for you the point. They mark for you the node of the model where your function had to visit before we are allowed to make a move from W to U, like that. So there is much more condition on the past history, and here you sort of see where you must actually have been before. So maybe it's even suggestive to have it to make this construction for finite mode. So, but the original constructions were Berlucci and Sharukov were for infinite reserve models, and this one.
Yeah.
Then they sort of understood, Sambel and Japaridze, that one can actually work with finite models as well, and things will only be simpler. So that's the history.
Okay, thank you very much.
Okay.
Okay, so
Thank
that's
you.
it. Thank you. So next week, probably next week.